Okay, so now that we have started recording, let me just, for the sake of the camera, so to speak, let me repeat what I said about negative Z values a while ago. A negative value of Z simply would mean that the voltage is opposite the current. That's all there is to it. Now, that seems a bit unusual, especially given the fact that we always know that current flows from high to low and stuff like that. But you should realize that in Z parameters, you get two of the Zs which are not really impedances. Z11 and Z22 are actually impedances in the effective circuit. Z12 and Z21, on the other hand, are actually ratios between voltage, controlled voltage sources and current somewhere else. In fact, that is exactly why you need control sources there, because here the voltage depends on a current somewhere else, and so you cannot really replace that by a impedance, or you cannot represent that by an impedance. So typically the negative value will occur either in Z12 or in Z21. Okay, and in fact, for many passive circuits, it happens all the time. Now, all that is telling you is that the sign of that voltage is negative if I say if the corresponding current in the other end is positive. Okay. Right. So that was the answer to the first question. The second question, unfortunately, I apologize for not being able to take a look at the discussion forum yesterday. But ideally, you should really not be solving the problem on the last day. So these questions, at least you should take a look at the questions beforehand and ask questions if you have any. But that's just an excuse. But okay, I should have actually taken a look at the discussion forum. Two of you asked exactly this question about negative Zs. And the other question, which was, it was written not to use the equations. Which equations are being referred to here? Those expressing V1, V2 as linear combinations of I1 and I2. Exactly. That exactly is what I meant when I said do not use the equations. Okay, I thought that would have been sort of obvious, although I could have been clearer, of course. Note that what you really have, okay, let me just go on to the actual, let me start sharing my screen first. I hope all of you can see now my screen with a piece of paper on it.
Yes, sir.
Okay. Now, there's one major problem, which is the program that I use, Zunal, has suddenly been updated. And they have done something which I guess they thought was nice. But as a result of that, the cursor has become tiny. So because it's a tiny cursor, I am finding it difficult to figure out where exactly on the piece of paper I am. But anyway, let me just remind you that when you started, basically what you had was capital V1 as some complicated function of I1, I2. Could be complicated, could be simple, but that depends on actually exactly what your circuit is like. And V2 as some other function of I1, I2. And then we did Taylor expansion and we wrote V1 equals, basically V1 is the change in capital V1 that will be essentially the partial derivative del V1 del I1 times change in I1 and so on. And this ultimately gave rise to this set. And V2 is Z21 I1 plus Z22 I2. So this is the equation or equation. This is the pair of equations that I'm referring to in the context of Z parameter equivalent circuit. So basically, you have this equation. What we do is we convert this equation into a circuit. That is, you say, okay, you are going to get a voltage of V1 across the input terminal. So this is going to be V1. Of course, this is really not the voltage. It's a variation of the voltage that we are talking about here. But we will essentially adopt this picture. We will say, okay, there is a bias, some kind of voltage and current set up in the circuit, which is the so-called quiescent point. And then we have fluctuations over that. When we say we are dealing with the AC model, we essentially ignore the quiescent point value and then look at what happens beyond that. So small v, if you want to implement this particular equation, what do? You say, okay, V1 is a sum of two voltages. Because it's a sum of two voltages, it has to be a series. And since Z11 I1 is one of the two voltage drops, with I1 the current flowing in here, this has to be an impedance. And then the other term, Z1 to I2, is one thing which you simply cannot implement with an impedance, simply because the voltage is here and I2 is in the other terminal. So what you do is put it as Z1 to I2 control source. But because this is a controlled voltage source, okay, a current controlled voltage source, Z1 to the P factor it has the dimensions of an impedance, but it's not really a passive impedance of the kind Z11 or Z22 on the other side is. So it could very well be negative. That was the answer to the previous question. And here, in this particular part, what we meant was you can either use this set of equations, these two equations, or use the equivalent circuit, both of which are exactly the same. The advantage of using the equivalent circuit is simply that you can actually make use of circuit analysis results like series parallel results or other things. And that often gives you better understanding of what is going on rather than just the equations. So very often, in fact, this is something we are going to do very often. Very often, the behavior of a circuit or a circuit component would be replaced essentially by, could be replaced by some complicated equation to begin with. Then usually we will do some kind of approximation and start with a simpler equation. And then once we have the simpler equation, we would try at least to change that into an equivalent circuit. Because once you have an equivalent circuit, you can use all kinds of circuit analysis tricks on it. Okay? So that is the reason why you would like to use equivalent circuits. And the question really said, do not use the original equations, just use the equivalent circuits. Okay, any further questions?
Sir, excuse me, sir.
Yeah. Could you be
Sir,
a
I have
bit
a
louder?
yes, sir. Sir, I have a
Yeah.
question regarding the derivation of the Z parameter
Yeah.
equations.
Go ahead.
Sir, so in the derivation, you had assumed an AC model, and then you had the derivations involved fluctuations in voltage and currents.
Hmm.
However, we are applying the same equations for problems which do not involve AC currents. Like all the problems in the problem sheet as well as the example
Exactly.
which we had shown
Okay.
were all DC. So I couldn't understand how we
Good.
can
That
use.
actually is a very good point. Uh, if you look at the derivation, what you have, okay, this is a very important one. The reason why I call this an AC equivalent model, and is basically because if you look at the mathematics of it, what you say is you start with two complicated functions that I wrote down a while ago. V1 is V1 of I1, I2. This may be a very complicated function, but not always. If you have a linear circuit, like the ones you had in an assignment, this would really be another simple function. Then you said, okay, there are some currents and voltages which are there in the circuit anyway. So without a signal, so you will say they are I1, let's say they are I1 0 and I2 0. And this will give rise to a value of V1, which is so-called the no signal or quiescent point value. You could also write that as V1Q, I guess. Okay, for quiescent point. And then you talk about what happens when the voltage, or rather what happens when the current I1 changes from the I1 0 value, the so-called DC value, by a small amount. I2 changes. And then you say, okay, if that happens, then of course V1 changes from its value V1 0 to a new value V1, and this V1 to first order in the Taylor expansion simply is del capital V1 del I1 evaluated of course at I1 0 I2 0 times small I1 plus del capital V1 del I2 small I2, and this of course gives rise to the Z parameter equivalent model. Now, as you rightly point out, we did not use small fluctuations in the assignments at all, and we did not talk about DC power or AC power. Now notice that the reason why we have to talk about the DC and the AC power, especially the reason why you have to talk about small fluctuations, is simply this. This equation for V1, okay, this is the problem. I've lost my cursor completely. I don't know where, here it is. This equation for V1, okay, is actually an equation which can be very complicated depending on what circuit you're dealing with. Okay. If it is, it will be very difficult to use this directly. That is why we talk about small deviations from whatever steady value you have. On the other hand, if the equation is linear to begin with, the voltages themselves are linear, or voltages are linear functions of currents, which happens if you use resistances and inductance and capacitance and other linear components only in your circuit, then of course what you can really do is just talk about this equation directly as a linear equation. So you could actually use capital V1 is Z11 capital I1 plus Z12 capital I2. That is exactly what has been done in the assignments. Or you could just say this. All we are doing is we are actually using our quiescent point values as 0. So no currents to flowing, no voltages. That's your quiescent point value for these problems. So small I1 is actually the same as capital I1, so everything goes through. Now you might say, why can we use this? The answer simply is as follows. Look, the reason why we talk about biasing, and once we have a quiescent point value, then we talk of movement away from it, is simply that as long as, say, the V1 could be a rather complicated function of I1, I2. So it could have, of course, if you really wanted to plot it, you would have to plot a surface in 3 dimensions, some complicated behavior like this. But in the neighborhood of any small point, this complicated surface would look flat. So those of you who have done some kind of analysis on 3D or analysis on RM would immediately know what we are talking about. This is what is called a tangent plane to the surface. But all this really means is a small enough part of any complicated surface, as long as it's a smooth surface, looks like a flat region. So that's, but it might very well be that in this region the things changes so rapidly that treating it like a flat region is bad. Here on the other hand, treating it like a flat region is a decent approximation. So sometimes you may have to choose your quiescent point carefully. In fact, in an actual amplifier application in transistors, you would actually have to set your quiescent point currents and voltages just right, so that when you change the currents a small amount from the quiescent point value, the voltages will change in proportion. You know, basically what you want is an amplified version of your input to occur at the output. But you don't want a distorted version. You don't want something which does not look like your input signal at all. So you want a proportionality. For that, you may have to actually choose your quiescent point value at some point. And that is how this system is actually used most of the time. Because this, frankly, Z parameters, Y parameters, H parameters are not used to study the kind of circuits that we have given you as an example. But that's simply because we have not gotten to those complicated circuits where you will absolutely need to use Z parameters or Y or H parameters. Things like things like transistor circuits, for example. Now there the quiescent point is essential because you have inherently non-linear behavior in your circuit, and you want to ensure that you are in a roughly linear region. You are in a region where currents and voltages are, at least fluctuations in current is proportional to fluctuation in voltage. Okay. Now that is why you need a quiescent point value, and that is why you need fluctuations around that. For a linear circuit, on the other hand, the kind we have given, this equation is actually exact. It's not an approximation. This result, V1 equals Z11 I1 plus Z12 I2 is exactly true. Just like in Thevenin equivalent. Remember, for a linear circuit, the Thevenin equivalent is an exact result. The same here. And in the circuit that we have given you, the quiescent point could be chosen anywhere, simply because for a linear circuit, it doesn't really make a difference what your quiescent point is. Because Z11, Z12, Z21, Z22 will not depend on your quiescent point choice. For linear circuits, they're just constants. And so that is the spirit in which we have used those problems. In fact, what you could say is that we have chosen the quiescent point or the DC point at 0 current, 0 voltage. So the actual currents and voltages are actually the fluctuations because they are the deviation from 0. Okay, does that answer the question?
Yes, sir.
So the advantage there is the Z parameter equivalent model is exact. So no approximation whatsoever. On the other hand, you don't really need to use Z parameter equivalence in such problems really. Okay, that's like a sort of an overkill. In Bengali, we have a saying, using a cannon to kill a mosquito. I'm pretty sure that an equivalent saying is there in every language. Using the Z parameters to solve the Wheatstone-Bridge problem is a typical example of an overkill. You don't really need it, but you can use it. Later on, when we talk about transistor equivalent circuits and so on, especially when we talk about design of the CE amplifier, the common emitter amplifier, there this will be very, very important. And there, we will really be talking about a true AC equivalent model. By the way, when I say AC, please don't imagine immediately that you get a sinusoidal variation like you see in your AC chapters in your textbook. Here, AC means any fluctuation from the DC value. Well, the name AC is fine because if DC is your average, then the fluctuation has to be both positive and negative, right? Because the fluctuation has to average to zero. So in that sense, it's AC. But it's not necessarily a nice sinusoidal signal. Often it is, but it doesn't have to. Okay. Any other questions?
A question.
Go ahead.
So you said that these are only this is actually an tangent plane which we are taking as an approximation for small i's. So
yeah.
sir,
small I1, small I2, right?
So I was actually thinking about it, sir. So sir, how would it help? Say I have a circuit and I only have an ammeter and an voltmeter to analyze it, and I want to know the output signal. Say if I give it a function f as an input, I want to know what the output function g will look like. So sir, how will this this approximation, this linear approximation, which includes which is for small change in the AC current, help in that case, sir? Because I want to know the whole function. I mean, I want to know the function globally. So how will that help, sir?
First of all, that may be too ambitious a project, right? You have to realize that science, and especially physics, is about things you can measure and control, not about what you want. Okay? That is a very important point, actually. You may not even be interested in the function globally. Like, say, if you have an amplifier, you know that you're going to give an amount of current. You give too much input current, your signal is going to saturate and sit at a fixed value. You don't really want to use that. Okay? So, frankly, in most situations, these work just fine because of the limited needs that people have. People don't really need to know the global function because first of all, a global function may be way too complicated to make sense out of. Okay. So let me just give you an example, a slightly different example. The pendulum, the simple pendulum, for example. Okay. Now many of you should already know that a simple pendulum is anything but simple, especially if you go out of this small amplitude approximation. Now, you can get an exact solution for the x as a function of t for small amplitude oscillations. You all know that. But even for large amplitude oscillations, you do get an exact solution. An analytic solution which is global. It's in terms of elliptic functions of the second kind. Now, that may sound very impressive, but is it useful? The answer is most often no. Sometimes it is, but most often, knowing an exact analytical solution or knowing a global solution is actually pretty useless. This fascination with exact solutions is unfortunately a result of the kind of training you have always had. You have always been trained to look for exact solutions because that's what the books tell you, and that's what you would want to find out in an exam, for example. But let me just point out that even for classical mechanics, which by the way is not a dead subject at all. In fact, most of the major amount of work in physics in the last, say, 30, 40 years has actually happened in classical mechanics, not in quantum mechanics or quantum field theory. A much bigger amount of work has happened in classical mechanics. But there, the whole focus has changed. You no longer look at individual solutions. You look at global behavior. You want to figure out how things would behave, okay, rather than exactly where the particle is at this point. Now, in electronics, also, very often we don't really care so much as to what will happen for all currents. We care about, this is my quiescent point. If you vary the current beyond in this neighborhood, how would your output behave? Simply because that is where you're actually going to use the system. Remember, electronics is very much of a real science in that sense that you don't really care about all possibilities. Although your question is, of course, could be very important for somebody who wants to use a circuit over a wide range of currents. There, of course, these models will not help you. Or actually, these models will help you. These models will help you to get a first approximation, but then you will have to change the quiescent point. Say suppose you are. So the curve might look very different. Suppose you have a V versus I curve, which looks like this. And there are circuit components for which the V versus I curve does look like this. So the behavior here would be like a negative impedance. Here it would be like a positive impedance. Here it would be like something where the voltage is almost flat. Now, if you use a single Z parameter equivalent model for all quiescent points to describe this, so suppose your quiescent point is here, then your model will give you a very good explanation of what happens close to this point. So if your I fluctuates slightly, you get a very good explanation. But then, if your I fluctuates this much, then the Z parameter model here will give you completely wrong results. Okay. Now this is the kind, remember in science we do controlled approximations. We do approximations with the full knowledge that we are approximating. So if your approximation fails, you should know where to look at. What kind of things could have gone wrong? Of course, you could use a Z parameter model with quiescent point here to describe things around this. Another Z parameter model with quiescent point here to define Z parameter values to explain situations here. Another one to explain situations here. And another one, yet another one to explain situations, say here. Okay. Entirely different looking tangents to this curve, entirely different looking Z parameter equivalent models. And that's fine. By putting together the information from each of these, you get a very good idea about what the thing is going to be like. Now, if you want a precise analytical function, most likely you will not get it. Analytical functions don't really describe, say, they describe only 0.0001% of the world or something. Most of the world is not described by analytic functions which are globally valid. Of course, you should be able to write down a function, but that could be done experimentally. Say you just use your voltmeter and ammeter, keep on measuring at different values. You may end up with a very complicated function in the end, or most likely will end up with a very complicated set of graphs. It may be very, very difficult to make sense out of what you see after that, or use it in a real situation. And that is why these approximate models actually are way more useful than the global model. Of course, you would also have to be very careful. You know that these are approximates. You know that they have limited range of validity. So you don't really try to use them global. So you would be right in saying, what good will this do to me if I want the global answer? The answer is not much. But frankly, you almost never want the global answer. You want local answers. That's the most common thing. Okay? So I hope I've made myself clear about this. Yes?
Yes, sir.
Okay. So if you really want the global answer, frankly, hard luck. This method will not give you that. It's not designed to give you that. It's definitely, in fact, it deliberately goes away from the global answer. Because the global thing is complicated. You just look at things locally. You look at things when current changes slightly. And that makes life a lot easier. Of course, especially when I say easier, I mean that you get linearized equations, which you can then model with simple equivalent circuits. And so then you can use your circuit analysis tricks, which is the real advantage here. Okay? Okay, anything further?
Sir,
Yeah.
can
Yes.
you check the diagram in the discussion forum?
Sorry, could you just repeat more
Can you
loudly?
check the diagram in the discussion forum?
Diagram in the discussion forum. Let me just check. Can I check it? Which one was this? I can't see any diagram.
In the
Or
Niveda,
this. There is a diagram. Okay, fine.
it seems that date 1 2 equal to date 2 1 in the problem in the slide.
You got Z1 to equal to Z21. You might have. Look, I am very bad at doing algebra, so I may have made a mistake. But most likely, in this case, you may have made a mistake about the signs. Or I made a mistake in drawing the signs. So check that carefully. When you say V1, which end is plus, which end is minus, remember we have redrawn the circuit drastically, right? So be careful about which end is plus, which one is minus, and so on. I would be surprised if you really got Z1 to equal to Z21. You got it most like, I can't guarantee that what I have done is right because my algebra is messy and wrong often. But this is a pretty standard result, so I don't think I am the one who got it wrong. Check again. We will discuss this later as well. But I think you have made a mistake in choosing the signs. Okay? Possible. But I will have to check. I can't answer this right now. Unfortunately, I have not seen this before. As I said, I couldn't really take a look at the discussion forum yesterday. But it's possible that you may have mixed up one or two of the signs. Okay? Be very careful because the sign convention has already been established when you wrote down the this full two-parameter equivalent thing. And that is important. So I'm not saying that what you're saying is wrong. All I'm saying is it's likely that it's wrong. But I will take a look at it. But it may be better if you took a look at it again and looked at the sign conventions properly. This is something which people get confused about all the time. So it's important to actually take a look at it very, very carefully. Okay, unfortunately, I can't give you any better answer right now because I'll have to work it out myself again. And I don't want to do it in front of you because almost certainly I will make a mess and make an even bigger fool out of myself. So I don't want to do it here. But do check. I think you have got a sign error yourself here. In one of the two calculations, of course. Not in both, because if you had got a sign error in both, then the overall thing would have again come out right. Okay, then. And this is exactly why I don't want the recording sometimes, because I might very well be saying completely wrong things right now, which are going to be recorded for posterity. So, if you are looking at this later, please remember that what I am saying here might very well be wrong. You should check yourself. Okay. Then now I'm surprised that there are no further questions because this particular topic is very, very complicated comparatively compared to the ones which you have done before. If there are none, then we are going to move on to the next topic where I am going to ask questions. Usually that threat almost always gets somebody or the other to ask a question. So I'm just waiting. Okay. I'm not sure, but have you actually watched the last lecture, lecture 4? Because at the end of lecture 4, there is something which is a bit unusual, which I'm pretty sure you will not find in a textbook or you have not seen before, the so-called extra element theorem. In a sense, it's a pretty exciting thing because circuit analysis was thought to be a dead subject in the sense that all that there was to be learned about it had been learned. And then somebody comes along in the last years of the 20th century and suddenly discovers an entirely new technique. I've just given you a very simplified version of the extra element theorem in that lecture, simply because I did not want to go into the full details that would take even almost a whole course. But it's actually a very exciting new way of calculating things. And you may want to take a look at it, some of you at least, not everybody perhaps. Take a look at it. You may, the place to start, of course, would be the internet. Just look for extra element theorem. You will find quite a lot of references if you are interested. Because it's a rather interesting and pretty amazingly fast and illuminating way of calculating results. Anyway, moving on. So now it's my turn to ask questions. But okay, today I'm not going to ask you very difficult questions for the time being. First of all, I want to establish the level at which we are, because we are going to next move on to AC circuits. And for that, using complex numbers will be essential. So let me just quickly ask you. Everybody is, of course, familiar with complex numbers. That's not a question. But when somebody says the current in a circuit I is I0 e to the power I omega t. So this is a typical thing that people say when you're talking about an AC. Current is I0 e to the I omega t. What does this mean? So that's the question.
Oscillatory current.
No, but does it really mean that current is I0 e to the I omega t? This thing is a complex number, right?
The real part is the current is I naught into sine omega t is the
by the way, nobody,
cos
of
omega
course,
t is the comment.
nobody really writes I, they write J. For the simple reason that I has, at least in electrical circuits, I has already been taken up by current. So J, of course, is square root of -1. So what you're saying is you just look at the real part. That is, this quantity is just this, J I0 sine omega t. Actually, this may not be right. Can anybody tell me why? Even this statement that I've written down on the board, on this piece of paper right now, may not be correct. Can anybody tell me why this may not be correct? Or at least this may not be correct in the sense that this may not give you the correct real and imaginary parts. This is mathematically correct, but if you want to look at the real part, then that may not be I0 cos omega t. And anybody tell me why?
Sir, is it
Maybe
actually
I
the
naught is complex.
Yeah, right. I naught here may be complex. So I naught, this could actually be something like magnitude of I0, which is really real. So if I naught were something like this, then this really would be I naught cosine omega t plus phi plus j into I naught sine omega t plus phi. Right? Because then I naught e to the j omega t will really be magnitude of I naught e to the power j times omega t plus phi. And then using Euler's wonderful formula, this is the result that you really get. Now, as well being said, we will take the actual current is not the whole thing, it's just the real part. Okay, or actually could be just the imaginary part, but everybody uses the real part by convention, so it is the real part. That's what we are going to use. But can anybody tell me why does this work? That is, why are you just allowed to use the complex current and then take the real part? Anyway?
Sir,
The reason is
orthogonality?
because the differential equations are real and linear, I guess. So both the real and the imaginary parts of the complex number satisfy the equations.
Okay, that's actually the wonderfully correct answer, depending, of course, on the systems that we are talking about. Very often we deal with linear circuits. Okay. And because we deal with linear circuits, there what you are saying is perfectly correct. Your equation, most physics situations actually have real equations. Imaginary numbers don't really enter directly into a physics equation unless you're talking about quantum mechanics, which is a different story altogether, where imaginary numbers play a huge role anyway. But in classical physics, anything other than quantum mechanics, complex numbers really are not there in the actual physical system. So your equations only deal with real numbers, and they are usually linear differential equations, at least, or linear algebraic equations, at least as long as you're using linear components like resistors, inductors, capacitors, and so on. So the basic idea is, if anybody asks you why does this work, the answer is that's just maths. What I have written down on the screen right now is this equal to this has a real part of this, which is of course nothing but math. This works trivially. But the real question here is, we do all kinds of manipulations with this current and simply forget about the fact that it's really the real part that we are dealing with. We actually use the complex current everywhere. And in the end, even in the end, we don't often use the real part of the answer. We just say the answer is a complex number, assuming that everybody understands that when you say the voltage is this particular complex function of time, you are supposed to take the real part. But why does this work? The answer is because your equations almost always are real linear equations. Linearity is extremely important because if you have linear equations, the real part does not mix with the imaginary part. So both the real part and the imaginary part separately satisfy the equations that you're dealing with. So instead of using the complex function, you actually get to use the real part without any problems whatsoever. You might, of course, ask, why would anybody want to then use the complex functions in the first place if it doesn't really make a difference? Why not just use cosine omega t plus phi? That is what you have, right? You don't really have a complex current. So why don't you just use I equal to I0 cos omega t plus phi and forget about complex numbers and all those complications? Why do you want to use that? Why would anybody want to make life complicated and deal with complex numbers when you don't need to? Quantum mechanics is a different story. There you need complex numbers. Here you don't. So why use them?
They make the calculations easier.
Yes. Why
Like
use it?
the use of complex number makes the calculation like easier when we can easily differentiate, integrate like based on
Now
the need.
I'm worrying whether I've got disconnected.
Like we can use because they make the life simpler by like simplifying the calculations. We can easily divide, multiply, subtract. Like they are easy to work with.
Yeah, tell me. So am I disconnected or is nobody in the mood to answer?
Sir, sir, can you hear us?
They make the calculations easier. We can integrate. Yeah, that's a wonderfully correct answer. Okay, I think somebody was perhaps using the chat even before that. Maybe you can't hear us. Okay, that might be a possibility. Can you try repeating? Somebody tried speaking now? And let's see.
Am I audible?
Yeah, now I can hear you.
Okay.
Okay, maybe my microphone got loose. Okay, that might be a possibility. Okay, so the reason why we use this, as Pradeep has typed out, I'm pretty sure somebody said this before, that the reason why we use complex functions is complex functions are much easier to use mathematically, especially e to the power j omega t exponential has very nice properties when you divide, multiply, and so on. So this is the real reason why you actually use complex numbers. Now, we will have a lot of occasion to use complex numbers in calculations. We will not talk so much about phasor diagrams because we have already studied about phasor diagrams earlier. But let me just point out that phasor diagrams, when you first study them, say in class 11 or 12, there very often people don't really mention the math behind it, but the math behind it is pretty straightforward. So if you were to, for example, write this I equal to I0 to the j omega t, algebraically, of course, that's what you have, but when you try to represent this graphically, what would happen is the point I0 e to the j omega t would actually be a point on the complex plane whose distance from the origin would be mod I0, and this angle would be omega t plus phi. That's a single point at a given instant of time. Okay? But as time goes by, what happens to this picture? What will happen to this point as time goes by?
Rotate.
Yeah. As time goes by, of course, t will increase to omega t plus phi. This angle will increase. So we will be going around in a circle. Okay. Of course, my drawing is pretty skewed, but what I really mean is a circle which is centered at the origin. It will keep on going around that very rapidly. Of course, depends on the value of omega. So that's what the complex geometrical version of this picture I0 to the j omega t being the current really looks like. Of course, as you all know, the actual current is really not this. The actual current is simply the projection which this point has on the horizontal axis. So as the thing goes round and round, this keeps on going back and forth. Okay, that's the oscillatory behavior that you expect. Okay, but the important point is something like this. Suppose I have this RC circuit, let's say. then the equation which this circuit obeys is of course something like this. Got it. Equal to whatever input E that you have here, some sinusoidal input. Okay. Now, if I is like I0 to j omega t, then Q, the integral, would simply be I naught by j omega e to the j omega t. And this whole equation ultimately will boil down to and this, of course, as you all know, is the complex impedance that you use for this circuit. The whole point is integrating the current to give you Q simply becomes a division by j omega, simply because that's all this really does for you. Okay. And now, what this means is E is simply the current times the complex number. Now, when you multiply a complex number by another complex number, there's a nice geometrical meaning to that. All that it does is the magnitude of this R plus 1 by j omega c is a factor by which the length of the complex number or the distance of the complex number from the origin would change. And then, since R plus I by j omega c, 1 by j omega c is not a real number but has its own angular part, so to speak, that will cause a change in the angle of E. So E would somewhere be like this. E would be somewhere here, let's say. So this is your I, this is your I, this is your E.
Excuse me,
So
sir.
is the screen not visible?
Yes, sir. You stopped sharing the screen.
At which point? Okay.
Sir, just a minute ago.
Okay. And by the way, if that happens, don't bother typing on the chat. Of course, you may want confirmation from your fellow students that has happened to everybody, but it's better that you just speak up, because especially when I'm sharing my screen, I may not be able to read the chat. Okay, so the E actually makes a bigger, in this case, a bigger angle with the horizontal axis, simply because R plus 1 by j omega, sorry, I got this wrong. This is perfectly wrong, completely wrong. In this particular case, R plus 1 by j omega c, oops, this cursor is really giving me trouble. I will have to find out ways of increasing its size. I can't see the cursor, so I can't even see where I am writing. This is a magnitude, then there's an angle of its own. Let's call that. But this angle is negative, right? Because it's really R minus j by omega c, and that gives a negative phase angle. So E will not be up ahead of, it will not have a bigger angle, or it will not make a bigger angle with the horizon than the current does. It will actually make a smaller angle. So E will be somewhere here. Its magnitude will be a multiple of the magnitude of I0, and its angle will be smaller, by this phi RC. Now, this is a static view of the thing, but what really happens is both the current and the complex point representing the current and the complex point representing the voltage, both of these would be spinning around rapidly, right? As t goes by. So the actual geometrical picture would be a dynamical one where I goes round the origin, so does E. And of course, the actual I and the actual E, the real current and the real voltage, would be projections of those spinning points on the horizontal axis. Now, because here E has a smaller angle, or E is making a smaller angle with the horizon than I is, what will happen is E, whatever changes will happen to E will happen a bit later. That is, the current will go, when will the current go through a peak, by the way? When the spinning point moves, when will the actual current go through a maximum? The complex point, of course, has no maxima or minima, but the actual real part, when will that go through a maximum? As this point spins around?
Sir, when the current phasor is on the real line.
When it's just on the horizontal axis, right? When it's just crossing the real line, right? That's when this projection is the largest. When it just crosses the real line again on the other side, you get a minimum. And when it just crosses the vertical axis, although my picture doesn't really show it properly because it's off center, there you get zero projection, right? That is, then the current will be going for zero. So of course the current goes to a maximum, then to zero, then to a minimum, then back to zero, then back to a maximum. It keeps on oscillating, the standard sinusoidal oscillation. But if you look at this picture, you will see that as the things spin around, which one will cross the horizontal line first, current or the electric or the voltage? Just imagine the picture spinning around. Which one will cross the horizontal line first?
The current.
Yeah, the current is actually here. So when both of them spin, of course, when the current gets here, the voltage is here. When the current gets here, the voltage is here, and so on. So when the current crosses the horizontal line, the voltage is still down here somewhere. So the current goes to a maximum before the voltage does. And you can easily see that this happens throughout. So current goes to a zero before the voltage goes to a zero a while later. Then the current goes to a minimum, the voltage goes to a minimum a while later because it's following it around, right? So this is what we mean when we say behind the current. So both the current and the voltage are sinusoidals. They oscillate, they go through a maximum, zero, minimum, zero, maximum, this whole cycle. But the current does so a bit earlier, the voltage does so a bit later. And usually you don't say voltage lags behind the current, you just say voltage lags. That's it. Okay, here you say the output. Or you could, in this case, say something like, this is, of course, voltage lags behind the current, but this is the input voltage that we are talking about. Okay. What about the output voltage? You may ask questions about that. But this lags, leads, etc. is simply easy to understand from this picture. Now, the phasor part of it is simply something you obtain by freezing this picture. In fact, that's exactly what we have drawn, because I couldn't draw a spinning I and spinning E on your screen. So what I drew was I and E for a particular frozen instant of time. One instant is like a snapshot, just at one instant of time. And that exactly is what a phasor diagram really is. Of course, you can draw parts of it, like you draw the part which is proportional to the resistance, which will be in the same direction as the current. Same direction simply because the resistance has no phase angle. So when you actually draw it, unfortunately, my drawing is hampered even more by my inability to see what's going on. Still, if this is your I, the current, this is the current, but of course, what you might want to talk about is the voltage across the resistance, which will be in the same, will have exactly the same phase. So it will be something like you would say V R. Then you can talk about the voltage across the capacitance, which actually is 1 by j omega c. Sorry. And because of this 1 by j, which is actually to the minus j pi by 2, right? That's what minus j really is. 1 by j is minus j, and that's it is a minus j pi by 2. That means that this particular piece has a, oops, not a very good drawing, but let me just. So this is what capacitor voltage would look like. And then you would join these two ends, and this will be VR plus VC. And of course, VR plus VC is simply the total input voltage, E. But all we are really doing is plotting the corresponding complex numbers on an Argand diagram, or this diagram that where you draw complex numbers on a plane. And instead of plotting that as time goes by, which would make the whole picture spin round and round, you plot it at a given instant of time. That's how you get your Phasor diagrams. So I'm pretty sure all of you have seen Phasor diagrams before. But what they really mean is simply nothing but a geometrical representation of complex numbers involved, nothing else. Okay, any questions on this? So if there are none, okay, let me just. So everybody knows this, right? This is something which is well known to everybody. If there's, okay, whenever I ask a question like that, if there's somebody here who is not familiar with this, please speak up. I'm assuming everybody is familiar with this. Fine. But then I have a question for you. Here this says the current leads the voltage, right? Or that's all fine. So the current goes through a maximum before the voltage does. It goes to a minimum also before the voltage does, and so on. But let me ask you this. Suppose I just switched on the circuit. Okay. So does the voltage across the capacitor, here for example, you can see that the voltage across the capacitor lags behind the voltage across the resistance by 90 degrees. So there's quite a lot of lag there. But when you just switch on the circuit, at that instant, voltage across the capacitor is zero, voltage across the resistance is also zero. So what happened to this lagging behind? Remember, when you say voltage across the capacitor lags behind the voltage across the resistor, that means that both of them will go through a maximum or will go through a zero, but the capacitor voltage will go through a zero 1/4 of a time period later. That's what a lag by 90 degree means, right? But when you just switch on an RC circuit, voltage across the resistance and voltage across the capacitance are both zero at that time. So how is that consistent with the voltage across the capacitor lagging behind the voltage across the resistor?
This is for the steady state condition. Like what you are asking about is for like the transient state. Like it takes some time to establish.
Okay. Is everybody here familiar with the transient state and what happens? Again, the question means the question simply means if you did not understand the answer that was given right now, would you speak up?
Yes, sir.
Okay.
I couldn't understand.
Yeah, the basic point that we are trying to make here is this. The solution that we wrote down, which essentially gave us E equal to I into R plus 1 by j omega c, this actually is not the actual solution to the differential equation. The differential equation, which is, of course, this does not look like a differential equation simply because I have not written it that way. but this really is 1 by c times q plus r times dq dt. Right? This is the differential equation. Now, when you solve a differential equation, you get two parts. Now, one part is called the complementary function. The other part is called the particular integral. Okay, do you always get that? The answer is no. You get this for linear equations or linear inhomogeneous equations. That is to say, if you were to solve this equation, you all know this, right? You have done this in differential equations. You solve this part, the solution that you get is what is called the complementary function. Now, the complementary function does not satisfy the equation at all, right? Not the equation you want to solve. It does not solve q by c plus r dq dt equals e. It's all the simpler equation, but it's not a solution at all. Particular integral, on the other hand, gives you a solution to the inhomogeneous equation. It gives you some current or some charge in this case, which if you were to plug into the equation would exactly give you E. So the question is, if the particular integral already gives you the solution, why do you need to worry about the CF at all, the complementary function at all?
Sir, because the particular solution is not the most general solution. It does not have the arbitrary constant in it.
Okay, and why is that a bad thing, not having the arbitrary constant of integration?
Because that doesn't take into account the initial condition given by the problem.
Exactly. The point really is the particular integral is called particular integral because it's particular. It doesn't have any arbitrary constants in it. Now, if you don't have an arbitrary constant in your solution, the trouble is you will not be able to fit the initial conditions. So your problem has an initial condition which has to be obeyed. That cannot be handled by the particular integral. That can only be handled by having a solution which has arbitrary constants in it. Q by c plus r dq dt equal to 0. If you solve that equation, you are going to get a complementary function which has an arbitrary constant in it. That's easy to see because if any q satisfies this equation, because it's a linear homogeneous equation, homogeneous meaning you have a 0 on the right hand side, any multiple of that q will also satisfy the equation, right? Because if q gives you 0 and you multiply q by 10, let's say, 10 times q is going to give you 10 times 0. This being a real linear equation, more important linear equation, 10 times q will immediately give you 10 times what q gave you. That is 10 times 0. And 10 times 0, of course, is 0. Right? So, if you find any solution to this equation, you can multiply it by an arbitrary constant. It stays a solution. So, now your complementary function gives you a solution with an arbitrary constant. Of course, the trouble is it doesn't even give you a solution to the equation you want. The particular integral gives you E, but you cannot multiply the particular integral by a constant and claim that that's going to be a solution, because if a particular integral has been obtained which gives you E, 10 times that particular integral will not give you E, it will give you 10 times E. And 10 times E is not what you want E. But the beauty is, if you add up the complementary function with the particular integral, the result that you are going to get is what the particular integral gives you plus what the complementary function gives you. The particular integral gives you E, which is already what you want. The great thing is the complementary function gives you 0. So E plus 0, of course, is 0. Sorry, E plus 0 is, of course, E. So adding the complementary function to the particular integral gives you a solution, because it does give you E when you put it into the equation. And on top of that, it gives you an arbitrary constant because the complementary function has an arbitrary constant. The advantage is you can use it to actually fit the initial conditions. Now, what has all that got to do with what I've said here? The answer simply is this. this solution that we wrote down, I equals E by divided by R plus 1 by j omega c, that actually is the solution which comes from the particular integral. It has no arbitrary constants, everything is fixed. That is not the full solution. The full solution is that plus the complementary function. Okay. So that's point number one. So the actual solution to this problem is always a sum of two terms. One is what you get using these complex impedances and so on. But that's a particular solution to the differential equations, not the full solution. The full solution will have that plus the complementary function piece. But the question now is, if that is the case, then why can we get away by saying that E equal to I into R plus 1 by j omega c? That's what we do, right? When we analyze an AC circuit, that's what we always say, or at least almost always say. Yes.
Sir, maybe because the transient part very rapidly goes to 0.
Well, not maybe. The point really is the other part, the complementary function. I'm not calling it the transient here because we have not justified calling it the transient. We are going to do it now. The point is the particular integral is a solution that your complex impedances, etc., will give you. What about the complementary function? That satisfies this equation, right? Q by C plus R dq dt equals 0. In this particular case, all of you should know the solution, what the equation is and what its solution is. It's nothing but the equation of a discharge of a capacitor, right? And you should all know its solution. Oops. So this solution is an exponential decay, and as a result, after some time goes by, e to the minus t by RC becomes nearly 0, so this part simply vanishes. So in the long run, the complementary function plus particular integral, which is the actual solution, is one in which the complementary function dies down completely and you're left with the particular integral alone. So what you have got is steady state. Okay. In any circuit which has a resistive behavior, which has some kind of dissipation, this complementary function will actually die down. It will just be some kind of damped oscillation or damped decay, as in this case. And in the long run, you will not have the complementary function any longer. You will just have the particular integral left, which is why the particular integral, the kind that we have written down here, is what is called the steady state solution. This is what happens to a circuit a long time after you have switched it on. That is long time after the effects of the initial conditions have washed away. Remember, the initial conditions can only help you manipulate the complementary function, right? The particular integral has no arbitrary constant, so you cannot, that doesn't change when you change your initial conditions. The initial conditions are taken care of by the complementary function part. And since it dies out with time, the effect of the initial conditions go away over time. And in the long run, you actually just look at what is left, which is a steady state behavior, which is just given by the particular integral. Okay. And that is also why this complementary function is called the transient. Transient in English is something which only stays for a time. And that's what happens to the particular integral. It only stays for a time. Oh, sorry, that's what happens to the complementary function. It stays for a time and goes away. Okay. Now, having said that, can anybody now answer the question? If that is really true, then why should we at all worry about the transients? Well, let's just make an estimate here. For example, if you are using an RC circuit with a resistance of 1 kilo ohm and capacitance of 1 microfarad, then RC, the product is just 1 millisecond. Kilo into micro is a milli. Okay. So that means that if you go to tens of 20 milliseconds, e to the minus t by RC will be so small that you will not be able to see its effect at all. Okay. So 10 to 20 milliseconds after you switch on your circuit, your complementary function goes away. You're just left with a steady state behavior. So if that is really the case, why worry about the transients at all? Yes? Why can't we just forget about the complementary function and deal only with the particular integral? I mean practically, not as a matter of solving a mathematical equation, but in dealing with what matters. Does the transient at all matter?
Yes, it matters like on a very brief period of time.
Yeah, but it only matters for a brief period of time. So who cares? Maybe it just, I will just worry about what happens after that. Right?
Yes, we can do that, but unless like we are asked to like what happens just immediately after we like switch on a circuit,
Yeah.
then it
Now
matters.
that
But
of course, once again,
after like
that answer is right, but again, I would like to point out that that answer sounds more like if in an exam somebody asks you what happens right after the circuit was switched on, right? Does it
yes,
really have any bearing on real life? That's the question I really mean. Physics, after all, is a real life science, and electronics even
no,
more so.
no, in
Which
real
they
life
don't
it
matter.
like it doesn't matter.
Anybody with a difference of opinion? Because look, a lot of effort has to be spent in studying transients. Transients are more difficult to study than the steady state behavior. So you might even say, why bother? If it's not going to be useful at all, then who cares?
So
And
it
that would be,
depends on the
yeah, that depends on.
that depends on the kind of signal that we have. So for example, if E behaves in a certain way that battery is switched on and off after certain intervals, then we need to care about the transient in order to study the behavior of the circuit.
Yeah, but even then, you are right in a sense, but even then I would say that transient would only sort of affect the behavior for 10 or 20 milliseconds, let's say. Can't we just ignore that? One case where we cannot ignore that is exactly what you have said, but not just when we switch on or off, but when we switch on or off rapidly. If say the rate at which, suppose E is not a sinusoidal signal, E is a pulse which comes in and goes away. And if the time duration of the pulse is say 5 milliseconds, then what happens for 10 milliseconds or 20 milliseconds is actually very, very important. So it depends, of course, that depends very much on your circuit needs. You may be using a circuit to actually detect a pulse coming from a charged particle moving in a cloud chamber, or, well, some esoteric particle which just got created in your Large Hadron Collider that gives you a very brief electrical signal. Of course, when your electrical signal is very brief, when you want to study it, you need to figure out exactly what happens in brief instead of time. Then the transient is not something you can ignore. That is really a very important point. So it depends on the time scale. If the scales at which your signals change is very, very small, your signal may simply go away after that. So it may not never reach steady state simply because there's no steady state to reach. You would have to be very interested in the transients. And that's exactly what we do in all kinds of high-speed measurements that we do. But there's another very practical reason why you might be interested, in fact, why you have to be interested in transients, even for standard circuits, even circuits where signals stay for a long, long time. So your transients would die out a long time ago and you would get to a steady state. Can anybody tell me why would I be interested in a transient even then? Even when our signals do survive long enough for us to actually reach steady state and we are really interested only in the steady state. Despite that, transients are important to study. Can anybody tell me why? Well, the answer is actually very simple. The answer is just this, that transients may last for a very short time, but they may be huge. Depending on your circuit, sometimes you may end up with very, very huge transients. Now, your circuit will get to steady state and you will be able to enjoy all the simple calculation or the results of your simple calculation, provided your circuit survives till the steady state. If your transient is so huge that it burns up your circuit, then saying that it stays only for a short while doesn't really help. Your steady state behavior will do you no good if your circuit has burned up before it got to steady state. And that might very well happen in a badly designed circuit. So you have to pay a lot of attention to the transients simply to ensure that your circuit actually survives. Remember, when you rapidly change signals over a short period of time, when you switch something on or off, very often huge currents or huge voltages are developed in your circuit. And that might damage your circuit. So just for the sake of safety or sake of ensuring that your circuit actually can get to steady state so that your simple calculations do work, you have to understand transients too. Okay? Is it understood? Now I'm feeling that I've been cut off. Again. So on my screen, it seems that I'm still connected. Am I?
Yes, sir,
Yes.
you are online.
Yeah. Okay. So there are two major reasons why one has to worry about transients. One is when your signal is very brief in time, then you have to worry about that. And the other is when your signal may be steady and exists over a long, long time, but your transient may be huge enough to damage your circuit, and that is a real concern. That's a very real concern. So we will explore steady state behavior most of the time, but in the assignments, we will also talk about transients a bit. The transients are really important. Okay, finally, okay, one more question about this. So when I try calculating the power through a circuit, what you do is you multiply the voltage by the current, right? But since voltages and currents fluctuate, right? In an AC circuit, what you really look at is the average power. So for the average power, you just integrate. So what you do is, say the current I is I0 into the j omega t. That's a complex current, of course. The voltage will be I0 times the impedance, whatever the impedance is, into the j omega t. This, for the RC circuit, could be R plus 1 by j omega c. Then the power is simply I times V. So that's so that actually fluctuates rather rapidly. In fact, fluctuates at twice the frequency as the current and the voltage. So usually what you're interested in is the average power. So this is the power. But instead of looking at this fluctuating power, you look at the average over a cycle, which means you have to integrate this thing over one cycle and then divide by the time period. So basically, it's really PT dt over one total cycle, 0 to capital T, where capital T is the time period, 2 pi by omega, and then divide this by time. So that's the definition of the average power. Now, if you were to calculate this quantity, you're going to get 0. It is about 2j omega t. Okay. When you integrate that, from 0 to 2 pi by omega, so simply going to get 1 by 2j omega And then that's either 2j 2 pi by omega. So 2j omega but this is nothing but e to the 4 pi j, which is also 1. Look at 0. Remember, we are talking about any z, not necessarily just 1 by j omega c, but z could be r plus 1 by j omega c, or r plus j omega l plus 1 by j omega c, or some other complicated combination. So my question to you would be this. Does this mean that in an AC circuit you never have any power? At least never have any power dissipation on average.
No, sir.
So what's wrong with this?
So it actually means that for the first quarter, the energy basically is increasing, and in the next quarter, it's getting away and into the source again.
True, you're right, but that would mean that on average, you're saying that you will get positive power for one part of the cycle, negative power for another part of the cycle. And on average, it's going to vanish, right? So the positive part and the negative part are cancelling each other out. So you're right in saying that the power is not zero instantaneous, but is the average power zero? That's my question. That's what I've just calculated for you. All I've done is started with the current, which is this. Then the voltage, which is the current times the impedance, whatever the impedance of your circuit is. Then you multiply the two, you get the power. That's the instantaneous power. And then when you take the average, you end up with 0. Now, you're right in saying that sometimes it's positive, sometimes it's negative. But if it's 0 on average, what that means is if you wait for many, many cycles, you're going to get 0 power. That would have solved our energy problems like anything. That no circuit would have, no circuit, at least no circuit working on AC, would have lost any energy. So you would not really need to supply more energy. You just start it once and you're done. Now you should know very well that that's not really true. So what is wrong with this calculation that I've done? That's my question. This is actually a very, very important point. So I'm hoping that everybody has got the question properly. If you have difficulty understanding the question, please ask. Yes? So did everybody understand the question first? So at least tell me whether you did, because I'm not, again feeling that I'm speaking to a void here.
Yes, sir.
Yes, sir, meaning what? You understood the question.
Yes, sir.
So what is the answer? And I've already told you the answer, but before, when we started, well, I didn't tell you the answer. Somebody among you people told me the answer. Why does the question, why is it legitimate to use complex numbers when you know that the current and voltage are very well real? What was the answer to that?
To simplify the calculation.
Oh, to simplify the calculation is why you do it, but what justifies it? You can't do something just because it simplifies the calculation, right? You only do correct things.
Because the differential equations are linear.
Well, not just the differential equations. Differential equations is just part of the story. The point is the operations that we are carrying out are linear. That is why real part and imaginary part stay separate. Okay, they don't mix up. No problems whatsoever. Okay. The trouble here is the moment we multiply current by a voltage, that's no longer a linear operation. You're multiplying two things. Okay. And as a result, you're making a mistake right at that point. If you say power is current times voltage, you're perfectly right. Power is current times voltage. But what power isn't is that it's not the complex current times complex voltage is real part. Why? Because you all know this, right? If you have one complex number Z1, which is x1 plus iy1, and another complex number Z2, which is x2 plus iy2, the real part of the product Z1, Z2 is of course not equal to the real part of Z1 times the real part of Z2, right? So real part, right, because the real part of Z1, Z2 is actually x1, x2 minus y1, y2. That's not real part of Z1 times real part of Z2, which is just x1, x2. Real part of I times V is not equal to real I, real V. So here the left hand and right hand sides are different. So which one of them is the actual power? Instantaneous power, which one of them? The left hand side or the right hand side?
The right hand side.
Yeah, the right hand side, real part of I is the actual current, real part of V is the actual instantaneous voltage. We tend to forget about the distinction between the complex current, complex voltage, and the real current, real voltage. But you have to be, that's because when we deal with linear calculations, it doesn't really matter. At the end of the calculation, you always can take the real part. But here, when you're multiplying two quantities or when you're squaring them, this actually makes a difference. You cannot multiply the real part of I and real part of V. In fact, you can multiply the real part of I and real part of V to get the power. In fact, that's exactly what you have to do. But that is not the same as multiplying the I and V together and then taking the real part, which is exactly what we did here. In fact, we did not even take the real part. We just multiplied I and V together to claim that this is the instantaneous complex power with the understanding that you take the real part at the end and you get the actual power, which is completely wrong. Okay. So this calculation, which tells you that the average power is 0, is wrong simply because you have made a very fundamental mistake. You have forgotten that when you're using complex currents and voltages, that's being used as a tool that simplifies, but only simplifies linear calculations, does not simplify calculations which involve linearity, nonlinear effects. Any nonlinear effect, your calculation cannot be done this way. Got it? So that was a mistake that we made. You cannot simply multiply the complex current and complex voltage. What you have to multiply is the instantaneous real current and instantaneous real voltage. Okay, and then do the calculation. Okay, anything else? Any further questions about this? Okay, I hope everybody has gotten the point. Whenever you have nonlinear operations, you can't do this. And that is why, that is one of the reasons why small signal AC models are so important. Because we will treat, well, because we have signals, we have sinusoidal signals coming in and going out, you will actually use complex currents and voltages a lot, even in nonlinear circuits. But you are really not going to use it in a fully nonlinear circuit, because there this calculation is completely wrong. What you will do is you will linearize the circuit. You will take small signal approximations so that the actual complex nonlinear circuit is replaced by a small signal linear equivalent. The whole point of carrying out Taylor series and keeping only the first order terms is that you're linearizing the problem. In that approximation, using this kind of complex currents and voltages make perfect sense. Okay. And there is another major reason why small signal approximations are what you really need to deal with. Global approximation, of course, they want global answers, but usually there's no easy way of answering that. For that, you will have to actually take recourse to a computer, for example, to do the complicated calculations for you. Okay, but what we should really do is at least say what the actual correct answer is. And there, the real part of I, which is well, that's wrong. It's not into the I phi 1. It's real part of I is, of course, mod I0 cosine of omega t plus phi 1. Is cosine of omega t plus phi 2, where phi 2 minus phi 1, the phase difference really comes from the factor z. It's really the phase part of z. So these are the actual currents. Although we are calling this a real part of I and real part of V, these are really the actual I and actual V. And the power is simply mod I0, mod V0, cosine of omega t plus phi 1. That's the instantaneous power. That one is positive part of the time, negative part of the time, because of the presence of the cosines. But now note that what's going to happen is when you integrate this P of t over the entire time cycle and take the average, then you have to integrate this product of cosines. Now, I'm not going to insult your intelligence by telling you how to integrate the product of cosines. Of course, you change it into use the product to some rule and so on. But when you use the product to some rule, one of the terms will have omega t plus phi 1 plus omega t plus phi 2. That's a cosine A plus beta. You'll also get an A minus beta. And the A minus B term does not have an omega t in it. That's a constant. The constant, of course, averages to its value. The other term, which has cosine 2 omega t in it, will oscillate rapidly. You'll have positive and negative terms, and that will just cancel. So your result actually is going to be and this is actually what you call IRMS, PRMS, cosine delta phi, where cosine delta phi, the phase shift between the power, between the voltage and the current is actually equal to, is what is called the power factor. Is you're getting IRMS into VRMS. Remember, IRMS is actually mod I0 by root 2, VRMS is mod V0 by root 2. The two root 2s take 1 by 2 in front. And cosine phi 1 minus phi 2 gives you the extra factor which you multiply the current times voltage by, the RMS current times RMS voltage by, and that's called the power factor. So this is the actual result of the calculation. you have to take the real parts of I and V first and then work out the answer. There is, however, another way of getting the answer, which is, remember, this is cosine of phi 1 minus phi 2. So if you just took the complex conjugate of V, which will give it e to the minus I phi 2, and e to the minus I omega t, multiplied by I, that would just cancel out the omega t term, and then you can take the real part of that. That actually gives you this result. Okay? Actually, half of that, because that actually would give you mod I0 mod V0 into cos delta phi. So half of this result. So the point is, you cannot really use a complex current and complex voltage to calculate the power. However, you can actually calculate the power by taking the real parts first, multiplying and then integrating. And the final answer happens to be something which you can write in terms of the complex currents and voltages. Because you're dealing with complex currents and voltages all the time, it is convenient to have a formula which just gives you the result in terms of complex currents and voltages without having to take the real part to begin with. But that result, that formula is derived by actually taking the real part, doing the messy calculation, the integration and so on, and then finally you arrive at this one result, which actually is very, very important. This tells you the average power through a circuit. It's not the real part of current times voltage, is half of the real part of the complex conjugate of V and I. Okay. Now, in particular, if you're talking about power dissipation across a pure capacitor or a pure inductor, then V and I have a phase difference of pi by 2 or 90 degrees. Cosine delta phi will be 0. So a pure capacitor or a pure inductor does not dissipate power on average. A pure capacitor, for example, charges up, stores energy, then charges down, releases energy. On average, it does not take any energy away. Of course, that's the case for a pure capacitor. If you have an impure capacitor, which also has some resistance to which current can leak, then the resistive part will still dissipate energy. But the pure capacitor or pure inductor part will not. But this is the final result that you are going to use often, this half of real part of V star I. But what is very, very important is that you have to realize that the way in which this calculation is done is different from the way in which you usually do calculations using complex currents and voltages, simply because this is a non-linear operation and the standard rationale of taking the real part after doing the calculation simply does not work. Okay? You will be used, the point is, complex currents and voltages are so useful that people don't really want to give them up. So even in non-linear situations, you will see people using currents and voltages which are given by complex exponentials. But then you have to bear in mind that every time you do the calculation, before you do a calculation, you have to take the real part. And that's very different from taking the real part after you do the calculation. Only for linear operations, it does not matter whether you do it before or after. And which is why for linear calculations, you can simply forget about the fact that the current really is a sinusoid and not a complex exponential, and do the full calculation, finally find the result out, and then be happy with your final result. I hope I have made myself clear here. Any doubts? Okay, if not, let's call it a day today. We will meet again on Thursday. If it's not Muharram, there is some doubt about whether Thursday is still a holiday or not. Okay. So if it is still Muharram, that is, if it is declared officially as Muharram, it says it's Muharram on our calendar, but there is some doubt about the exact date now. If it stays Muharram, then of course we will meet again next Monday. If not, you'll have to tolerate me on Thursday. Okay. I don't know that for sure now, but I'm sure the Dua or somebody else will come. If there's no notice, then it means that our calendar stands, which means on Thursday we will have no class. But I'm hoping that there will be a notice and things will change. Okay, any further questions? If not, we can just wrap up today. Okay, let's wrap up today.